Welcome back. In this lecture I shall discuss transmission and distribution of air. So, the specific objectives of this particular lecture are to present equations for estimating fan total pressure and fan power, to estimate friction loss in circular and rectangular ducts, to estimate dynamic losses through bends, branch takeoff and entry, sudden expansion and contraction, to discuss static regain factor, and finally to discuss requirements and general rules in duct design. At the end of the lecture you should be able to estimate fan total pressure and fan power from friction and dynamic losses, estimate friction loss in circular and rectangular ducts, estimate dynamic losses through bends, branch takeoff and entry, sudden expansion and contraction, explain the concept of static regain factor, and finally list the requirements and general rules to be followed in air conditioning duct design. So, let me give a brief introduction. An air handling unit, commonly called as AHU, transmits air from the plant to the conditioned space and distributes it within the conditioned space. So, this plays a major role in any air conditioning system, the AHU. A typical AHU consists of supply and return ducts with cooling and or heating coils, humidifiers, filters, etc. It also consists of supply and return air inlets and outlets. It also consists of supply fans and, if required, return fans. In an AHU, air is transmitted through various ducts and other components with the help of fans. So, we need fans to distribute and transmit the air. Since the fan motor consumes a large amount of power and the duct system occupies considerable building space, the design of air transmission system is an important step in the complete design of air conditioning systems. In order to design the system for transmission of air, it is important to understand the fundamentals of fluid flow. Basically, here the fluid means air through ducts and various components of the duct. So, let us look at the fundamental equations. These aspects I have discussed while discussing the fundamentals of fluid flow. Okay, so I assume that you still remember those things. So, straight away I go to the governing equation, which is called as modified Bernoulli equation. You must remember the assumptions under which the Bernoulli equation is valid. Okay. So, from for real fluids with finite viscosity, the modified Bernoulli's equation gives the head loss between any 2 points in the duct. Okay. Any 2 points 1 and 2, the head loss is given by this equation: P1 by rho z plus V1 square by 2z plus Z1 is equal to P2 by rho z plus V2 square by rho z 2z plus Z2 plus HL, where HL is the head loss. Here all the units, for example, this if you remember, is known as static head. This is your velocity head. This is head due to elevation. Okay. Similarly, this is the static head at point 2, this is the velocity head at point 2, this is the head due to elevation at point 2, and HL is the loss, okay, as the fluid flows from one point to the other. And here we call it head, if you remember, because all these parameters have units of length. Okay, that means everything is in meters if you are using SI units. And to overcome the head loss, a fan is required, because you can see that there is a loss of head because of the viscosity. So, if you want the fluid to flow, then a fan is required. And when you use the fan, you have to put in some work input, and the required power input to the fan is given by this equation: W subscript fan is equal to Q dot air into FTP divided by eta fan, where this is the power input in, let us say, watts, and Q dot air is the volumetric flow rate of air in meter cube per second, and FTP is what is known as fan total pressure in pascals, and eta subscript fan is the efficiency of the fan. So, if you know the volumetric flow rate of air, and if you can estimate the fan total pressure FTP, and if you also know the efficiency of the fan, then you can find out what is the total power requirement to run the fan. Okay, so this is one of the important objectives, because you have to finally select a fan, and you also have to find out how much power is required to run the fan. Okay, because you have to select a suitable fan motor. Okay. So, what is this FTP? How do we find FTP? The fan total pressure FTP is given by this equation. FTP is equal to P2 minus P1, that is the static pressure difference between point 2 and 1, okay, plus rho Vt square minus V1 square by 2z. This is nothing but the velocity pressure, difference of velocity pressure between 0.2 and 1, and finally difference of elevation pressure between 0.2 and 1. In most of the air conditioning calculations, this parameter is negligible. Okay, only in special cases this may have some effect, otherwise it is normally negligible. Okay, so basically we have to deal with the change in velocity pressure, change in static pressure, and finally the head loss. Okay, pressure loss due to friction and other factors. If in the duct, if let us say that the initial inlet static pressure is same as the outlet static pressure, then this becomes 0 because P2 is equal to P1, and if you are using a uniform cross section duct, then V1 will be equal to V2. If air is behaving as an incompressible fluid, then this factor also becomes 0. Then you find that the fan total pressure is nothing but the pressure drop due to friction and due to other factors. Okay, so to find out FTP, ultimately you have to find out the head loss. Okay, so that is what is mentioned here. To find FTP, the total pressure loss delta PT from one section 1 to other section, let us say 2, has to be estimated. So we have to find out what is the total pressure loss, and the total pressure drop or pressure loss is due to two factors. The first factor is because of frictional pressure drop, commonly called as friction loss, delta P subscript F, and the second factor is momentum pressure drop, or also known as dynamic loss, delta P subscript D. So you find the total pressure drop delta P subscript T is equal to delta P subscript F, frictional loss plus dynamic loss. Okay, so if you want to find out this, we have to first find out what is the friction loss, what is the dynamic loss, and if you add up, you find the total pressure loss. So let us look at the estimation of friction loss. Frictional pressure drop in ducts is commonly given by this Darcy-Weisbach equation. This equation relates the frictional pressure drop delta P subscript F with the velocity pressure rho V square by 2, friction factor F, length of the duct L, and diameter of the duct D. Okay, if you are using a circular duct, then this is the diameter of the duct. If you are using a non-circular duct, we have to use an equivalent or hydraulic diameter. Okay, so here V is the velocity of the air, rho is the density, and F, as I said, is the friction factor. Okay, and for turbulent flows, the friction factor can be evaluated using Colebrook and White equation. Of course, you can use several equations depending upon the type of flow. So most of the time in air conditioning ducts, the airflow is of turbulent in nature. Okay, so you have to use correlations for turbulent flow. Okay, for turbulent flow there are several correlations. In fact, I have discussed these correlations while discussing the fundamentals of fluid flow. Okay, so the most popular equation is what is known as Colebrook and White equation. That is what is given here. Okay, so you can see the Colebrook and White equation where F is the friction factor, Ks is the surface roughness of the duct and D is the diameter of the duct, and Re subscript D is nothing but the Reynolds number based on the diameter. So if you know the Reynolds number and if you know the surface roughness, you can find out what is the friction factor. Obviously Reynolds number depends upon the flow rate, diameter, density, viscosity, etc. So you know the definition of that. One thing you can observe from this equation, Colebrook and White equation, is that the friction factor appears on both sides, both left hand side as well as right hand side. Okay, so if you know the absolute roughness K subscript S and Reynolds number Re subscript D, then you have to use a trial and error method to find out the friction factor F. Okay, and as shown, the friction factor is a function of Reynolds number, hydraulic diameter, and inner surface roughness of the duct material, here K subscript S. Let me show typical surface roughness of typical duct materials. This table shows the absolute roughness of some of the materials which are commonly used in air conditioning ducts. First one is galvanized iron or GI sheet, so it has a surface roughness of 0.3015 meters. This is most widely used. Okay, sometimes concrete is also used, so concrete has a surface roughness which varies from 0.003 to 0.003 meter, and riveted steel has this roughness, cast iron has this roughness, and commercial steel has this roughness. Okay, so these are the materials which are traditionally used in various types of air conditioning ducts. However, nowadays people also use other materials like fiber plastics, and people also use aluminum, etc. Okay, they have certain other advantages. So when you are using these materials like aluminum or fiber, you have to use appropriate surface roughness. Okay. Now, what is done normally is, as I said, the GI sheet is most widely used. So, taking GI sheet as a duct material and properties of air at 20 degree centigrade and 1 atmosphere pressure, the frictional pressure drop in a circular duct is expressed by the following equation. Delta PF is the frictional pressure drop in Newton per meter square or Pascal. This is given by 0.022243 Q air to the power of 1.852 into L divided by D to the power of 4.973. Here, as I said, Q air is the volumetric flow rate of air in meter cube per second, okay, and L is the length of the duct in meters and D is the diameter of the duct in meters. So, this equation is valid only for circular ducts, okay, and this is valid strictly for GI sheet material and for air at 20 degree centigrade and 1 atmospheric pressure. And using this kind of an equation, friction charts have been created for estimation of frictional pressure drop of standard air through circular ducts made of GI sheets, okay. Standard friction, these are called the standard friction charts. Let me show one typical friction chart. So, this shows a chart for estimating frictional pressure drop in circular GI ducts. Here on the x axis you have pressure loss per unit length, that is delta PF by L, okay, pressure drop per unit length, and on the y axis you have the flow rate in meter cube per second, okay, and you also have constant duct diameter lines. These are the duct diameter lines, for example 0.35, 0.3, 0.25, these are all the duct diameters. You also have the velocity, constant velocity lines. These are the constant velocity lines, okay. For example, this one has 2 meter per second, 3 meter per second, 4 meter per second, 5 meter per second, like that, okay. So, using these friction chart, standard friction chart, you can find out the required parameters if any two parameters are known, any two parameters out of flow rate, duct diameter and pressure loss. For example, let us say that I would like to design a duct for a flow rate of 0.2 meter cube per second, and I would like to have a frictional pressure drop of 3 Pascal per minute, okay. So, that means I am fixing the frictional pressure loss per unit length and I am also fixing the flow rate. Then you can see that you have to choose these two lines. If you draw a vertical line like this and a horizontal line like this, they intersect at this point, and at this point the required diameter is 0.2 meters, okay. So, that means for this particular flow rate and for this particular frictional pressure drop, I have to use a circular duct of diameter 0.2, and at this point you can also find out the velocity. For example, at this point the velocity lies between this line and this line, that means between 6 and 7 meter per second. So, by interpolation you can find out what is the velocity at that point, okay. You can also do this problem in a different way. Let us say that you are fixing the diameter of the duct and you fix the flow rate, then you can find out what is the frictional pressure loss, okay. So, if you know any two out of these three, you can find out the third parameter. So, this is very useful and it is very commonly used in air conditioning duct design. As I said, these are valid for circular ducts only, okay. And for air at standard conditions, what happens if air is not at standard condition? As I said, the friction chart is valid for air at 20 degree centigrade and at 1 atmospheric pressure, but you may have a condition where the air is not at 20 degree centigrade, but it is at some other temperature, let us say 10 degree centigrade, and the pressure is not atmospheric but something else, okay. Then I would like to estimate the friction loss for these new conditions, okay, at different temperature and different pressure. Because of different temperature and pressure, the densities will be different, okay. So, if you take, let us say condition 1 as a reference condition, that means 20 degree centigrade and 1 atmospheric pressure, and condition 2 as the actual condition, that means 10 degree centigrade and some other pressure, and I want to find out what is the friction pressure loss at the off design conditions, okay. Then you can use the simple equation given here, which is valid for small changes in air density and temperature, okay. So, the relationship is like this. For variation density, delta PF1 divided by delta PF2 is simply equal to rho 1 by rho 2, that means delta PF is directly proportional to density. So, if I know delta PF1 and the density rho 1, and if I also know the density at off design actual condition rho 2, then I can find out what is the friction loss, okay, from the standard friction loss delta Pf1. Similarly, the relationship between the friction loss and temperature is given by this equation. It is inversely proportional to the absolute temperature to the power of 0.857. Okay. So, if I know this and this, then I can find out what is the friction pressure loss at a different temperature. Okay. And these are generally valid for small temperature changes and small changes in air density, which is an actual case in air conditioning duct. Okay. You do not come across very large temperature changes. The friction pressure drop equation and chart, as I have said, are valid only for circular ducts. Okay. For other shapes, for example, for rectangular duct or for square ducts, an equivalent diameter has to be used to estimate the frictional pressure drop. Okay. Let us see how to do this. First of all, let us look at non-circular ducts. The most widely used duct geometry is that of rectangular duct. Okay. Why rectangular duct is most widely used? Because these ducts are preferred as they occupy less space, because they match with the building. For example, you have a flat roof, then a rectangular duct matches with the flat roof better than a circular duct. Okay. So, that is the reason, that is one reason why rectangular ducts are preferred. A second reason is that it is easier to fabricate rectangular ducts out of sheet metals compared to a circular duct. Okay. So, the fabrication is also easy. Because of these two reasons, rectangular ducts are most widely used. However, from performance point of view, that means from friction loss point of view, a circular duct is the best. Circular duct is not used because of other consideration, not because of performance. Since a square comes closest to the circle, as far as possible, the rectangle should be as close to square as possible. Okay. So, narrow rectangles are not preferred. So, since rectangular ducts are most widely used, we would like to find out what is the friction losses in rectangular ducts. The equations and friction charts for circular ducts can also be used for estimating pressure drop through rectangular ducts by using an equivalent diameter. Okay. So, if you use an equivalent diameter in place of the circular diameter, then you can use the same charts and equation that you have used for circular ducts. What do we mean by equivalence? Here the equivalence requires that the volumetric flow rate and frictional pressure drop per unit length should be same for both circular and rectangular ducts. Okay. So, this is the condition for equivalence. So, if you apply the condition for equivalence, you can easily show that the equivalent diameter d subscript eq of a rectangular duct is given by this equation. D subscript eq is equal to 1.3 into AB to the power of 0.625 divided by A plus B to the power of 0.25, where A and B are the two sides of the rectangular duct. Okay. So, they are the two sides, and the ratio A is to B is called as aspect ratio. Right. So, if you know the two sides of the duct, then you can find out the equivalent circular diameter circular duct, which will give the same volumetric flow rate and also the same friction loss. Okay. So, that is what you have to keep in mind. And when using equivalent diameter and flow rate to find the frictional pressure drop from the charts, the velocity values shown on the chart are not the actual velocities. Okay. For example, let me show the. Let us say that as I mentioned earlier, this is valid for circular duct, this particular friction chart, standard friction chart. Okay. And I have a flow rate of 0.2 meter cube per second, same earlier example, and I have a pressure loss of 3 Pascal per meter. Okay. And I am using a rectangular duct. So, the rectangular duct should have an equivalent diameter of 0.2, okay, because this is where the two lines intercept. So, I should have a rectangular duct which has an equivalent diameter of 0.2, which I can get from this standard chart, but the actual velocity will not be between 6 to 7 meter per second. So, you cannot use the velocity values that you obtain from the chart, you can use only the equivalent diameter values from the chart. Okay. Then how do we find the actual velocities? The actual velocities can be found very easily from the flow rate and the actual cross sectional area of the rectangular duct. If you know the volumetric flow rate, then you divide the volumetric flow rate by the cross sectional area, that is nothing but A into B, then you get the actual velocities. This actual velocity will not match with the velocity obtained from the chart. Thus, from a known flow rate and allowable pressure drop, one can estimate the required equivalent diameter, as I have already explained. From the equivalent diameter, and either by fixing one side of the aspect ratio one can find the dimensions of the rectangular duct. Okay, so if you have to fix one more parameter, either one side or the aspect ratio, then you can find out the dimensions of the rectangular duct. Let me show a simple example. Again I use the same data, that means I have to design a duct which has a flow rate of 0.2 meter cube per second, and the allowable pressure drop is 3 Pascal per meter. Right. So, from this chart I find that the diameter of an equivalent circular duct is 0.2 meter. Okay. So, and from the equation, and I am also fixing the aspect ratio here, that means I fix that the ratio of A is to B is equal to 1:2. So, from this diameter value and this aspect ratio 1:2, if I use the equation for equivalent diameter, I can easily find out that the value of A is 0.13 meter and value of B is 0.26 meter. So, the rectangular duct having one side of 0.13 meter and the other side of 0.26 meter will give me this flow rate and this pressure loss per unit length. Okay, so, that is how you can easily find out the dimensions of the rectangular duct. And as I have already mentioned, the aspect ratio should be as close to 1 as possible for better performance. Okay. Aspect ratio 1 means it is a square. Okay. The cross section is square in nature, right. So, it should be as close to 1 as possible, and the equation for equivalent diameter that I have given in the previous slide is valid for an aspect ratio of 1:8, okay, less than or equal to 1:8. It is not valid if the aspect ratio is greater than 1:8, or it will give large error if you are using it for large aspect ratios. And in air conditioning ducts, normally you never come across a duct having an aspect ratio greater than 1:8. Okay. This is as far as the estimation of friction loss is concerned. Okay. So, once again I would like to repeat whatever I have said. First you have to find out the friction loss. For finding out the friction loss, normally the flow rate is known, and the length of the duct is generally known, okay, from the location of the inlets and outlets, etc. Then if you are using a circular duct, straight away you can use the friction chart or the equation, and you can find out what is the frictional pressure drop per unit length. Okay. So, if you know the length, then you can find out what is the total friction pressure drop. If you are using a rectangular duct, then first you have to fix either one side or the aspect ratio, and then you have to fix the allowable pressure drop, and from the allowable pressure drop and from the flow rate you can find out the equivalent circular duct diameter, and then using the equation for equivalent circular diameter and either the aspect ratio or one side you can find out the other side. Okay. So, that is how we can find out the frictional pressure drops. Now, let us look at the estimation of dynamic pressure losses. First of all, where do you encounter dynamic pressure losses? Dynamic pressure loss takes place as air flows through various fittings, bends, etc. In a typical air conditioning duct, we use a large number of fittings, bends, etc. For example, you may have to bend the duct by 90 degrees, by 60 degrees, by 30 degrees, depending upon the construction of the building and depending upon the duct layout. Okay, so air has to take a turn, right, whenever there are bends. In addition to the bends, you may have to enlarge the duct at some points, you may have to reduce the cross section area of the duct at some other points. Okay. So, that means air also undergoes expansion or contraction, okay, because of the change in the cross section area of the ducts. So, in these enlargements or contractions and in the bends, the air undergoes additional losses. Okay. These losses are known as dynamic losses, and these are also known as momentum losses, because here the pressure loss is because of the change of the momentum. Okay. Momentum changes because air either changes its velocity or changes its direction. Okay. And normally the fittings, for example bends, sudden enlargements or contractions, etc., are short in length, because rarely the length of these fittings exceed 1 meter. Since the length is small, you find that the pressure loss in these fittings is mainly due to momentum change and not because of frictional losses. Okay. That means major pressure loss is because of momentum, not because of friction. And in turbulent flows, it is observed that the dynamic loss is proportional to square of actually velocity pressure or square of velocity. So, that is given by this expression here. This is the dynamic pressure drop or dynamic loss, which is proportional to velocity pressure rho v square by 2. okay, and the proportionality constant K is known as dynamic pressure loss coefficient, right. So, if you know the dynamic pressure loss coefficient and if you also know the velocity pressure, then we can easily estimate the dynamic loss. Of course, the major problem or major task is to estimate the dynamic pressure loss coefficient, okay. So, once you estimate that, you can find out the dynamic loss. So, let us look at how to estimate the dynamic pressure loss coefficient for various types of bends and fittings. And sometimes what is done is an equivalent length L subscript EQ is defined to estimate the dynamic pressure loss through bends and fittings. That means what is done is, if you have, let us say, a 90-degree bend, okay, the 90-degree bend is equated to the pressure loss that takes place in a straight duct of the same diameter, but which has an equivalent length, okay. That means one bend, let us say that I say that 190-degree bend is equal to 20 meters of straight duct, right. So, this 20 meter is what is known as equivalent length of the fitting, okay. So, once I know the equivalent length, then I can use the friction charts, okay, standard friction charts or the friction equations to find out the dynamic loss, okay. That means I am expressing the dynamic loss in terms of a friction loss by using an equivalent length. The equivalent length obviously depends upon the momentum change and dynamic loss due to momentum change, etc., okay. That is shown here in this equation. The dynamic pressure loss is then obtained from the equivalent length and the frictional pressure drop equation or friction chart. For example, the dynamic pressure loss, which is actually given by K into rho v square by 2, and it is expressed as F into L equivalent divided by D equivalent multiplied by your velocity pressure rho v square by 2. So, you can see that from these two equations, the dynamic loss coefficient K is equal to friction factor multiplied by the equivalent length divided by the D equivalent length. So, if somehow if I know what is the equivalent length, then I can use the friction charts to estimate the pressure drop due to dynamic losses also, okay. Now, let us look at some individual fittings and bends and see how to estimate the dynamic pressure loss. First, let us look at the most common type of bend, that is known as 90-degree turn. So, dynamic pressure drop due to turns, bends or elbows, sometimes it is also called as elbows. And as I said, the most common type of bend is used as is the 90-degree bend, okay. So, this is what is shown here. So, this is called as a 90-degree bend because this angle, okay, this is 90 degrees. So, air enters like this, okay, then it takes a turn, a 90-degree turn, and leaves the duct like this, okay. So, you have to, for example, I have a duct, okay, and I have to suddenly change the dimension or direction of the duct. That means air has to come like this and it has to go this way. Then I have to use this kind of a fitting here, okay, so that air can come like this, take a turn and go this side. And this is where the dynamic pressure drop takes place, because air is changing its direction, okay. Air may not be changing its velocity, but it changes its direction, okay. And you can see from this picture that a 90-degree bend is specified in terms of the inner diameter, inner radius R1 and the outer radius R2, okay. Normally you do not have a sharp bend here, so you have to provide some radius here and some radius here. And what happens actually is that as the air takes a turn here, boundary layer separation takes place, okay. It starts somewhere, separation starts somewhere and boundary layer separates, and as a result you have a region, okay, where eddies are formed, okay, because of these eddies the dynamic pressure losses take place, right. So, the pressure here will be lower than the pressure at this point, right. And here I have shown a rectangular cross section, but you can also have a circular cross section, okay. You can have any cross section, right. This is what is known as a 90-degree turn, and we would like to find out what is the dynamic pressure loss as the air flows from point 1 to 2, okay. And the dynamic pressure drop due to 90-degree turn is expressed by this equation, delta P, D stands for dynamic pressure loss and B stands for bend, okay. So, this is general equation, this is valid for not necessarily 90-degree turn, but it is valid for any degree turn, okay. And Cb is what is known as the dynamic loss coefficient due to the bend, right. And rho v square by 2, as you know, is the velocity pressure, V is the velocity. And for 90-degree bend, the dynamic loss coefficient Cb is expressed as the aspect ratio W by H and inner and outer radii of the turn R1 and R2, and it's also available in the form of tables and graphs. Okay, so let me show a typical graph. Okay, so as I said, this is your 90-degree bend, and here the dynamic loss coefficient Pb, okay, is plotted on the y-axis, and on x-axis you have the radius ratio, that means inner radius divided by the outer radius of the bend for different aspect ratios. Aspect ratio means this W divided by H. Okay. So, what do you observe from this one? From this graph you observe that as R1 by R2 increases for a given aspect ratio, as R1 by R2 increases, the dynamic loss coefficient reduces and the pressure drop also reduces. That means you cannot have a very sharp bend here. It is better to provide as the higher radius as possible at this point. Okay, so if you increase the radius, the boundary layer separation is delayed and the eddy losses are also minimized. Okay, so the inner radius to the outer radius ratio should be as high as possible. Okay, and you can also see that for a given radius ratio, as the aspect ratio is increased, then the dynamic loss coefficient reduces. Okay, that means instead of having a large this thing, let us say that we compare two, okay, same width, different heights. Okay, so you find that this will give you less dynamic pressure drop compared to this. Okay, so that is what is obtained from this particular graph, and equations are also available for estimating the dynamic loss coefficient Cb in terms of R1 by R2 and in terms of the aspect ratio. So, as I said, the pressure loss increases as R1 by R2 decreases, and or the aspect ratio W by H decreases. Okay. So, what is normally done is normally turning vanes are installed in the bends to reduce the pressure losses. Okay. So, whenever you have sharp bends, you normally use a turning vane. So, what do you mean by a turning vane? This is a turning vane. Okay. So, instead of having an empty duct like this, they put some vanes here, so that air flows through these vanes. Okay. So, as a result of this, the dynamic pressure loss reduces. Why does the dynamic pressure drop reduces? The turning vanes reduce the dynamic pressure loss as it is equivalent to increasing the, I am sorry, this is a mistake, increasing the W by H ratio. Okay. So, the moment I am putting this one, that means I am dividing this portion into many small ducts, each having a same W but a reduced H. Okay, so you can see that W by H ratio increases because of the turning vanes. As a result, dynamic loss coefficient reduces and the pressure loss also reduces. Okay. So, this is as far as 90-degree turn or bend is concerned. In practice, you may also have bends which are not necessarily 90-degree bend. Okay, you can have a bend which is 30 degrees or 40 degrees or 50 degrees or whatever it is. Okay, you can have different angles. So, obviously, for these different angles, the dynamic loss coefficient Cb values will be different depending upon the angle of the bend. Okay, so ASHRAE data books and other air conditioning data books give charts for estimating dynamic pressure losses through bends as a function of the degree of the turn. Okay, that means angle of the bend, right, for different angles, 30 degrees, 45 degrees, 60 degrees, like that. Okay, so you have to refer to those data books to find the dynamic pressure drop in bends of different angles. Okay. Now let us look at branch takeoff. What do you mean by branch takeoff? These branch takeoffs are generally used for splitting the airflow. Okay, so let me show a typical branch takeoff. So this is the branch takeoff. Supply air, let us say, enters the larger ducts at this point. This is the upstream. U is for the upstream, and it flows through the duct to some extent. And at this point, I would like to split the flow. Right. That means I want to send some amount of air, let us say, to one room, and some amount of air to another room. Okay, two different rooms. So I have to obviously split the flow at this point. So whenever I have to split the flow, I have to use this kind of a fitting. Okay, so you connect the duct on this side, and you connect the duct which goes to this room at this point and which goes to this room at this point. Okay, so this is what is known as a branch takeoff. Of course, theoretically you can also have a branch takeoff of this nature. Okay, air can go this side or air can go this side. Okay. Now whenever you are using the branch takeoff, pressure drop takes place. Pressure drop takes place. Now you have some static pressure here, some static pressure here, some total pressure at this point, some total pressure at this point. But the upstream static and total pressures are same. You will also have different, you may have different dynamic pressures because the velocity here may be different from velocity at this point. That means pressure drop takes place as air flows from upstream to the branch and as air flows from upstream to the downstream. That means you can have delta P upstream to downstream, delta P upstream to branch, and they may not be equal. Okay, so we should be able to estimate what is the pressure drop from upstream to downstream, upstream to branch. Okay. So for the dynamic pressure drop from the upstream to downstream, that is delta P subscript U to D is given by this equation. Delta P U to D is equal to 0.4 multiplied by the velocity pressure in the downstream, rho Vd square by 2 multiplied by 1 minus Vd by Vu whole square. Okay, so here Vd is the velocity of air in the downstream duct and Vu is the velocity of air in the upstream duct. Okay. So you are using this equation, and if you know the dimensions of the duct and if you know the flow rates through each portion, then you can easily find out all these parameters and you can find out what is the dynamic pressure loss because of the branch takeoff from upstream to downstream. Normally it is observed that this pressure drop is very small compared to this pressure drop. Okay, that means the pressure drop, dynamic pressure drop from upstream to downstream is negligible compared to the dynamic pressure drop from upstream to branch. Okay, that is delta P U to B. Delta P U to B is given by this general equation. This is equal to the velocity pressure in the, I am sorry, this should have been B, VB, that means the velocity pressure in the branch multiplied by a dynamic loss coefficient from upstream to the branch. Okay. And obviously the major task is to find out this C U to B, and it is observed that the C U to B, that is the dynamic loss coefficient from upstream to the branch, increases as beta decreases. Okay. And as VB by VU increases, that means the branch to upstream velocity ratio increases, right, and these values are available in tables and charts. Okay. So if you look at any standard air conditioning design data book, you can find out this value as a function of this angle beta, okay, and as a function of this velocity ratio VB by VU. Okay. So this is for branch takeoff. Then you can also have branch entry. Okay, what do you mean by branch entry? These are normally used in return air ducts. Okay, let me show a typical. This is a reverse of branch takeoff. So here what happens is air from return air from one room, let us say located at this point, comes this side, this way, and from another room comes like this, and both return airs have to be mixed and sent to the cooling coil. Okay, so they are used in return air duct. So air is coming in this direction, air is coming in this direction, and it is getting mixed here, and the mixed air goes to the cooling coil, right. So this is known as branch entry, and again branch entry pressure drop depends upon what is this angle beta, what is the ratio of velocity VU by VD from delta P from this point to this point, and what is the velocity VB by VD for pressure drop from branch to the downstream. Okay, now this is upstream, this is branch, and this is downstream. Okay. And as I said, these are commonly used in return air ducts, and the values of dynamic pressure loss coefficients from upstream to downstream, that is C subscript U to D, and from branch to downstream, that is C subscript U to D, are available in the form of tables and graphs, and these are functions of upstream, branch and downstream velocities and the angle beta. Okay, so if you look at air conditioning data books, you can get this data. So once you know the, for these three types of, let us say, fittings, that is bends and branch takeoff and branch entry, the important thing is to find out the dynamic loss coefficient. Okay, once you know the dynamic loss coefficient, and if you also know the either the velocities or the flow rates and the duct dimensions, then you can find out the dynamic pressure loss, okay, because of the fittings, right. And you can also have other types of fittings, for example sudden enlargement. Okay. Let me show the picture of sudden enlargement. This is a sudden enlargement. This is not generally recommended, but sometimes you cannot avoid this. Okay. So air comes like this through a narrow duct, and suddenly it has to be enlarged. Okay, it enters into a large duct, let us say. Okay, so this portion is known as sudden enlargement. Okay, there is sudden change in the area. Because there is a sudden change in area, there is a sudden change in velocity. Okay, here the velocity will be much lower than the velocity in this point, because the flow rate is same. We are talking about steady flows. The volumetric flow rate will remain same. Since the cross sectional area is high, the velocity will reduce. Okay, for this kind of sudden enlargement, analytical expressions for dynamic pressure loss have been obtained using Bernoulli's equation and from conservation of linear momentum. Okay, of course, this analytical expression is subjected to certain assumptions, and the analytical expression is known as Boda-Kano equation. Okay, so the Boda-Kano equation gives the dynamic pressure loss due to sudden enlargement, that means from point 1 to 2, that is delta P 1 minus 2, right. So this is given by this equation, rho V1 square by 2, where V1 is the velocity before the enlargement, right, multiplied by 1 minus A1 by A2 whole square. Okay, so A1 is the area at this point, A2 is the area at this point. Okay, so A1 by A2 whole square. Obviously, A1 by A2 is less than 1, right. So as A1 by A2 reduces, you can find that the pressure loss increases. That means if you have very narrow portion here and very large this thing, okay, then obviously the dynamic pressure loss increases. And comparing this with your general equation, you find that here the dynamic loss coefficient is equal to 1 minus A1 by A2 whole square. Okay, as I said, this is an analytical expression subjected to certain assumptions, right. And this is a very famous equation, and it is called as Boda-Kano equation. And it is observed that from experimental results, that Boda-Kano equation is found to overpredict the pressure loss when the air flow rates are high and underpredict when the flow rate is low. That means it does not give you exact results either at very low flow rate or at very high flow rates. Okay. Of course, what is very low flow rate, very high flow rate is again a thing to be decided. Okay. But in general, in the absence of reliable experimental data, you can use the Boda-Kano equation, because all that you have to know is the area ratios and the flow rates. Then you can find out what is the pressure loss. Okay. However, for actual design calculations, they use a correction factor to this Boda-Kano equation, and correction factor again depends upon your area ratio, velocities, etc. So if you know the correction factor, then using the Boda-Kano equation and the correction factor, you can find out the actual pressure loss due to sudden enlargement. Okay. Similar to sudden enlargement, you can also have sudden contraction. Okay. Let me show a sudden contraction. Sudden contraction is this: air is flowing in a large duct, and suddenly it has to be, the cross sectional area has got to be reduced. Okay, so we call this as sudden contraction. And physically, what happens is when there is a sudden contraction, you find, for example, a streamline. Okay, let us say that streamline is flowing like this, and you have a sudden because of sudden contraction, there is a boundary layer separation here. Okay, and there is a region at which the cross sectional flow area becomes minimum, and that cross section is called as vena contracta, or that region is called as vena contracta, where the area of flow area is minimum, right. And what do you have above that? You have a region where you find eddies. Okay, so this is what leads to your dynamic pressure losses, right, the formation of eddies due to boundary layer separation, right. This is a very well known phenomena, the formation of vena contracta due to sudden contractions. And again the analytical expression subjected to certain assumptions is also known as Boda-Kano equation, okay, exactly like your sudden expansion, right. The Boda-Kano equation is given by this expression: the dynamic pressure drop due to sudden contraction is equal to rho V2 square by 2, that means the velocity pressure in the downstream, multiplied by A2 by A1 dash minus 1 whole square, where A2, as you can see, is nothing but the cross sectional area in the downstream, and A1 dash is the area of cross section at the vena contracta, okay, at this point, right. Obviously, A1 dash by A2 will be greater. I am sorry, A2 by A1 dash, A2 by A1 dash is greater than 1. So this will be greater than 0. Okay, so and when there is no vena contracta, then obviously this will be 0 and there is no pressure loss, but there will be pressure loss because vena contracta forms due to boundary layer separation, and this is generally written in this form. Okay, that means this A2 by A1 dash ratio is replaced by 1 by Cc, where C subscript C is known as contraction coefficient, which is nothing but A1 dash by A2. Okay. So, as I said, the coefficient C subscript C is known as contraction coefficient, and it is seen to be equal to area ratio A1 dash by A2, and A1 dash is the area at vena contracta, and values of contraction coefficient are available in the form of tables and charts. So, let me show a typical table. So, as I said, again this is the geometry, and this is the expression for finding the dynamic pressure drops, and if you know the contraction coefficient, then you can find out the dynamic pressure drop. Okay, because normally we know this from the flow rates and from the dimensions of the duct. So, here you can see the contraction coefficient is expressed as a function of downstream cross section area by upstream cross section area, that is A2 by A1. So, you can see that when A2 by A1 is very small, okay, the contraction coefficient is very small, as a result the dynamic pressure loss will be large. Okay, because the Cc is small means this is large, so the dynamic pressure loss will be large. So, as the area ratio increases, obviously the contraction coefficient also increases, and in a limiting case when the area ratio is equal to 1, that means there is no contraction but it is a straight duct, the contraction coefficient is obviously equal to 1, so that this becomes 0. Okay. Again, as I said, this Boda-Kano equation is an analytical equation. If you use right value of contraction coefficient, which is obtained from experiments, then you can use the Boda-Kano equation for estimating the dynamic pressure loss due to sudden contractions. Okay. Now, we may also have other miscellaneous fittings and openings, etc. For example, you can have abrupt suction openings. Okay. Suction openings means, for example, you have, let us say that you have a fan and suddenly air has to flow from a fan. Okay, you have the opening and suddenly it has to flow into this. Okay, so you have again a fitting here. So this is known as a sudden suction opening, or you can also have a flow in this direction. Okay, you have the fan sucking air in this direction, so suddenly air has to enter like this. So, for this kind of sudden or abrupt suction openings, the dynamic loss coefficient K is found to be about 0.85. That means the dynamic pressure drop delta PD, okay, is equal to 0.85 multiplied by rho v square by 2, where rho v square by 2 is the velocity pressure in this opening, right. Instead of sudden this thing, if you have formed entrance, that means air enters like this, okay, not suddenly, but air entrance in a formed or gradual entrance, then there is a dramatic reduction in the dynamic loss coefficient. It reduces from 0.85 to 0.03. That means the dynamic pressure losses are reduced very much. Okay, so as far as possible, you must avoid this sudden entry. So you must always try to use this formed or gradual entry. Okay. So for this kind of suction openings, you can use the dynamic loss coefficients and find out the dynamic pressure drop. For discharge openings, okay, that means you have the duct, okay, you have the, let us say you have the duct and suddenly you have the conditioned space, okay. So supply air is entering like this and suddenly it is discharged here, okay. So again there is a sudden change of cross section, and here this area is very large, okay, and here you have atmospheric conditions, pressurized atmosphere and something like that. So here you can't, strictly speaking, you can't use the sudden expansion this thing, because this ratio is very large, okay. For this kind of discharge openings, the dynamic loss coefficient is found to be equal to 1, because all the kinetic energy is simply dissipated, okay. So Cb is equal to 1 for this kind of discharge openings, okay. Now the total pressure drop for AHU equipment, we have to find out the total pressure drop for AHU equipment. Total pressure drop due through various cooling and heating coils, air filters, dampers, etc. They have to be obtained from relevant manufacturer's data, because it depends very much on the specific design of this equipment. So you have to use the manufacturer's data. Now let us look at like a factor called a static regain factor. What is the static regain? Whenever there is an enlargement in cross sectional area of the duct, the velocity of air decreases and the velocity pressure is converted into static pressure. Okay, so when you are enlarging, velocity obviously reduces because the flow rate remains same. So velocity pressure is converted into static pressure. The increase in static pressure due to decrease in velocity pressure is known as static regain. Okay. In an ideal case with gradual enlargement, when there are no pressure losses, you find that the static regain factor is equal to 1. Okay. That means this is the case where there is a increase in cross sectional area, but this is very gradual. Okay. The area is increasing very gradually. Okay, so gradual this thing. So as the area is increasing, velocity reduces, so the velocity pressure reduces in this direction. Okay, so this is the drop in velocity pressure delta PV, okay, due to enlargement. At the same time, there is an increase in static pressure, okay, because of the conversion of velocity pressure into static pressure. Okay, so this is the increase in the static pressure. Since this is an ideal enlargement, you find that the reduction in velocity pressure is exactly equal to the increase in the static pressure. As a result, the total pressure remains constant throughout. That means this is an ideal case where there are no pressure losses, right. This is an ideal enlargement. However, for sudden or non-ideal enlargement, you find that the decrease in velocity pressure will be greater than the increase in static pressure, and the total pressure decreases in the direction of flow due to pressure losses. Okay, for example, this is also an enlargement, but this is a highly irreversible type of an enlargement, that is a sudden enlargement. Okay, when there is sudden enlargement, there is a drop in velocity pressure. Okay, this is a drop in velocity pressure, but this is not converted into static pressure. Okay, or very less of it is converted into static pressure. So delta PV is much greater than delta PS. Okay, increase in static pressure is much smaller than decrease in velocity pressure. Okay, and you find that as a result of which there is a total pressure loss. Okay, so this a pressure loss takes place. This is equal to the difference between delta PV and delta PS, right. And the pressure loss here is due to separation of the boundary layer and the formation of eddies. And the pressure loss due to enlargement, delta P loss, is expressed in terms of a static regain factor R, and the static regain factor R is defined as the ratio of delta PS by delta PV. Okay. This is the ratio, that means the rise in static pressure divided by the drop in velocity pressure. Okay. So using the static regain factor, we can find out the pressure loss due to enlargement as 1 minus R into delta PV. Okay, delta PV is equal to PV1 minus PV2. Okay, where R is the static regain factor. Obviously, when for ideal enlargement, R is equal to 1, so delta P loss is equal to 0. For non-ideal, this thing R is less than 1, so there will be some pressure loss. Okay. Now let us quickly look at design of air conditioning ducts and what are the chief requirements of an air conditioning duct system. The chief requirements are that it should be conveyed, the air should be conveyed to the required locations at specified rates. This is first important requirement. Second requirement is that it should be economical in combined initial cost, fan operating cost and cost of building space. Okay, so this is the second requirement. Third requirement is that it should not transmit or generate objectionable noise. Okay, so you have to design it so that there is no noise generation. And generally at the time of designing an air conditioning duct system, the required air flow rates are known from load calculations. Okay, so we know the air flow rates, and the location of fans and air outlets are fixed initially depending upon the building layout, and the duct layout is then made taking into account the space available and ease of construction. Okay, so that means at the time of duct layout you have to have this input, right, and there are certain design rules which have to be followed while designing the ducts. What are the design rules? First rule is that air should be conveyed as directly as possible to save space, power and material. That means unnecessary bends, turns should not be there. Okay, you have to convey it as directly as possible, which will give rise to lower space cost, power cost and material cost. Second requirement is that, or second rule is that air velocity should be within permissible limits to reduce noise. You cannot have very high velocities or you cannot have very low velocities. And the third rule is that sudden changes in direction should be avoided, okay, because we have seen that if there is a sudden change there will be large dynamic losses, so this should be avoided. And when it is not possible to avoid sudden changes, we have to use turning vanes to reduce the pressure loss. And fourth rule is that the diverging section should be gradual and the angle of divergence should be less than or equal to 20 degrees. That means again this is from the static regain factor point of view, you would like to regain the drop in velocity pressure, so you have to have a gradual diverging section, okay. And the aspect ratio should be as close to 1 as possible, I have already explained this, and normally it should not exceed 4. And the duct material should be as smooth as possible to reduce frictional losses, okay. So these are the general rules to be followed. At this point I end this lecture, and let me quickly summarize what is that we have learned in this lesson. We have seen the equations for estimating fan total pressure and fan power, and then we have seen how to estimate friction loss in circular and rectangular duct. Then we have also discussed the estimation of dynamic losses through various fittings and bends, and we have also discussed static regain factor, and finally we have looked at the requirements and general rules to be followed in the design of air conditioning ducts, okay. So in the next lecture I shall discuss various duct design methods, okay. What are the different methods for designing the air conditioning ducts? Thank you. Welcome back. This lecture is a continuation of my earlier lecture. In the last lecture we have discussed how to estimate frictional and dynamic losses in air conditioning ducts, and I also mentioned briefly the design rules to be followed while designing air conditioning ducts. So the specific objectives of this particular lecture are to discuss classification of duct systems, discuss commonly used duct design methods, namely velocity method, equal friction method and static regain method, and then discuss briefly the performance of duct systems, and discuss fans and fan loss, and finally discuss briefly the interaction between fan and duct systems. And at the end of the lecture you should be able to classify duct systems, design air conditioning ducts using either velocity method or equal friction method or static regain method, then evaluate performance of duct systems, then discuss and use fan loss, finally discuss interaction between fan and duct systems. So let us first look at classification of air conditioning duct systems, how they are classified. Based on the load on duct due to air pressure and turbulence, duct systems are classified as low pressure systems wherein the air velocity is less than or equal to 10 meter per second and the static pressure is less than or equal to 5 centimeters of water column. These systems are known as low pressure systems. Then you have medium pressure systems where the velocity is still less than or equal to 10 meter per second, but the static pressure is between 5 centimeter to 15 centimeter of water. Then finally you have high pressure systems where the velocity is greater than 10 meter per second and the static pressure is between 15 to 25 centimeters of water column. Okay, so this is how normally the air conditioning systems are classified. Now, what is the effect of velocities? High velocity in the ducts results in smaller ducts and hence lower initial cost and lower space requirement. Since the velocity is high, for the same flow rate we can reduce the cross section area, that is how you get